Hi, this is Stephen Brower from Martin Valley Community College. I sat down actually to record my video on remove, and usually in the classroom, I go, remember last time in class I did? And they're like, oops, something I usually did on the board, I did not make a video for. So this really should be part of part one. Well, it should be. So first, as a review, binary search trees. Now I know this looks a little bit off, but from Apple's perspective, everything to the right is greater. So this is a binary search tree. There's nothing to the left of it. So APP, APR, the apricot is greater. From Lemon's perspective, everything to the left is less than or equal to it. From Lemon's perspective, everything to the right is greater or equal. And so from every node in the tree, it's the same thing. To the left is less than or equal. To the right is greater. To the left is less than or equal. To the right is greater. All the way down the tree. So this is a binary search tree. The reason why it looks funny the way it is more for part two when we get to remove. We'll see what happens if we try to remove Apple. So we'll visit that later. But before we can do remove, we have to do exists. Now exists wasn't listed on the UML for part one. And this is the kind of thing I usually will talk through on the board. And so let me just, let's just pretend I just wrote it on the board, but then we'll talk about what's going on here. Remember when we dealt with linked lists? When we dealt with linked lists and we needed to march down the list, we had a cursor, and then the cursor was starting off at head, and then when we were marching down the list, we would do something like cursor equal cursor get next. Well, the issue with binary search trees is we have both a left and a right. So if we decide that we need to advance, we need to figure out whether we're going to advance to the left or advance to the right. So cursor equal cursor get left or cursor equal cursor get right. Meaning, coming back to the tree here, if we start off and our cursor is here, if then we're trying to find, let's say we're trying to find grape, if our cursor is currently here, then we'd have to then do cursor equal cursor get right to this point. Again, suppose we're looking for grape and this isn't grape. Well, we now need to do cursor equal cursor get left to get to here. Again, if we're looking for grape, then cursor equal cursor get right, we get to here, and then we found it. One of the things that the exists has in tree that we didn't have in linked list is we need to determine, are we going to go left or right? So in terms of similarities, now this was deliberately written to be as close to the exists in linked lists. And so there's other ways of doing it, but I just wanted to do this one simplistically right now. And so cursor starts off at root. We have this Boolean found that we start off at false. Yeah, for the loop itself, well, not found, so we haven't found it, and while cursor is not null, meaning we haven't fallen off the tree, we compare cursor get data to target. Now, in this case, it was using compare to, but we also could have used equals. So this is, of course, left over from a prior semester. Remember, compare to will return if this here, if this is before this, it returns a negative. If this is after this, it returns a positive. If this is the same as this, it returns 0. So using the compare to, we could do cursor get data compare to target equals 0. And I think part of the reason why I'm illustrating it this way is because if we did equals, the next part, well, let's go and just do this again. So we could do it as equals. Okay, so cursor get data, equals target, then found is true. And so if we find it, we find it. If not, then here's the determination on whether we go left or not. And so I think the reason why I did have the compare to initially here is because when we do the compare to, we say, well, there's three possibilities. It's negative, it's 0, or it's greater than. And by showing, and I think I was trying to illustrate something when I did this previously. Let's put this back to the And if we are doing a compare to here, and this is taking care of 0, then we do the compare to here, then we're looking for one of the other two conditions. Compare to is one of those relative things. It's this relative to that. So cursor get data, for the node that we're pointing to, we're going to compare it to target. And if cursor get data is after target, then it would return something that's positive. And so if cursor get data is after target, that means we want to go to the left. The other thing we could have done, but this is PowerPoint, not NetBeans. The other thing we could have done is if we did it thinking this way, let's compare target to cursor get data. Then if it's less than 0, we want to go to the left. So we have to be very mindful when we use the compare to, what's to the left and what's to the left of the dot and what's in the parentheses. And it's always relative to this item first. So if this is before this, we get a negative number, which is why we're doing here less than 0. So yeah, I initially did have it written one way. That I'm not trying to confuse you. Well, I'm not trying to confuse you. I know I'm confusing you, but I just want to show that it does make a difference positionally, whether you do cursor get data dot compared to target or target dot compared to cursor get data. We have to make sure that this directionality goes the right way. Let's recap. We have a loop. We're moving cursor down the tree. So coming back here again, the idea is we're moving cursor down the tree. If we find what we're looking for, great. If not, we have to advance cursor either to the left or to the right. We have to advance cursor to the left or to the right. We have to advance cursor to the left or to the right. So we're moving cursor down the tree. Determining whether it's left or right, that's this piece right here. So this is determining, do we go left or do we go right when marching down the tree. So this exists method here, this is written iteratively. I may have another video later that has the exists recursively in BST node, but for right now, I just have this iterative right now. So now that we have this algorithm to look at, let's step through for exists. And what I'm going to do is, so there's these first two lines right here. Oh, well, there's something that's not showing. That's right. Well, we'll pull it off for right now. So let me get rid of this parent thing because parent doesn't apply. But suppose we are now, cursor is root. Suppose we call the exists method and we're trying to find kumquat. So imagine if target has the value of kumquat and cursor, so initially here cursor is the root. So is target kumquat equal to cursor get data apple? It's not. Okay, so this test right here, it's not. So then it comes here to the else. If target compared to cursor get data is before, well, target kumquat is not before apple. So so since it's not before, we come here, cursor equal cursor get right. So by doing the cursor equal cursor get right, is cursor moves to the right hand side. And so after that is done, we'll come back up. We still haven't found what we're looking for. Cursor is not null because cursor is now pointing to lemon. And so we come back in and we do the comparison again. So here is target equal to cursor get data? It's not. Is target, which is kumquat, before lemon? It is. So that means then the cursor has to do cursor equal cursor get left to move down to here. And so now we're back on the top of the loop. We're going to compare target to cursor get data. Are they the same? No. Is the target before this? It's not. So cursor will move to the right. Oh, doing a slight adjust. Sorry about this. To the right. And so now we're comparing again. Is kumquat Is the target kumquat the same as cursor get data grape? No, it's not. Is kumquat before grape? It's not. It's after. So cursor equal cursor get right. So cursor's here right now. And so we're comparing is target, which is kumquat, cursor get data. It's not. Is kumquat before cursor get data? Is it before kiwi? No. So then we'll do cursor equal cursor get right. Well, to the right of kiwi is nothing. And so what happens is this cursor becomes, oh, no. And I just give a little, so cursor becomes null. And so after advancing cursor to the right, so after we do cursor equal cursor get right, cursor becomes null. We come back up to the top here, cursor is null, and so then we exit the loop, we return found, which is false. So in this example right here, we were trying to find kumquat, and we didn't find it. I'm at 11 minutes. I'll just try a couple more searches, and hopefully maybe I'll do this a little bit faster than I did previously. We'll try. So I may go too fast. The nice thing about a video, you can always pause again. So we want to find apple, and so in the top of the loop, we're going to compare cursor get data and target. They're the same. We found it. Done. Okay. So one of the things I do want to point out is if we exit out of this loop, if we exit out of the loop and found is true, cursor is pointing to the node that we found. This is going to help us for when we do the remove. But when we fall out of the loop, cursor is pointing to what we were looking for. Okay. So let's do another search. So this, oops, we're trying to find raspberry. So does raspberry equal cursor get data? It doesn't. Is raspberry before apple? It isn't. So cursor gets moved to the right. Is raspberry cursor get data? It's not. Is raspberry before lemon? It's not. So we move this to the right. Is raspberry equal cursor get data plum? It's not. Is raspberry before plum? It's not. So we do cursor equal cursor get right. Is raspberry equal to cursor get data tangerine? It's not. Is raspberry before tangerine? It is. So cursor, whoops, cursor equals cursor get left. And so now the question is asked, does cursor get data, which is raspberry, equal raspberry? It does. So we found what we're looking for. So if we were searching for raspberry, we would come out of the while loop, having set found to true, and cursor would be pointing to raspberry at this point. Okay, last one. We want to find cantaloupe. So is target equal to cursor get data? No. Is cantaloupe before apple? It isn't. So cursor equal cursor get right. Is cantaloupe, or is our target equal to cursor get data? It's not. Is cantaloupe before cursor get data? It is. So our cursor moves to the left. Does the cantaloupe equal cursor get data? It does. We found what we're looking for. So the exists method that I just kind of jumped through, this exists method uses a cursor. It moves it down the tree. It either moves it to the left or it moves it to the right, depending on how what we're looking for compares to the data at the cursor. Okay.